So the first day of this virtual week, I want to make sure you're comfortable with parametric equations and their derivatives. So with parametric equations, you will be asked to find the first derivative and the second derivative, and then you'll be asked to use those derivatives to answer certain questions. So I want to talk about what the equations are, how you find it, and then what are some of the applications. Tomorrow's lesson will continue that and look at more motion-based applications. Today we're going to talk more like straightforward applications like slope and concavity, that type of thing. So when you have parametric equations, so again, our parametric equations are x of t and our y of t, and they are always presented as a pair. If you are asked for the derivative, which would be dy dx, it hopefully makes sense that you would take the y derivative in terms of t, so dy dt, and divide it by dx dt. And that will give us our first derivative, which can be used to find things like slope and tangent line. And eventually with motion, it will even talk about directional motion as well. So first derivative, really straightforward. You take the y derivative, put it on top. You take the x derivative, put it on bottom. Maybe there's a little simplifying you can do, often not. Maybe you have a point that you can plug in to go a little bit further and get a numeric value, but it's a very, very quick process. Second derivative is a little less intuitive and a little more that you have to kind of commit it to memory what you're doing. So if you're asked to find the second derivative, and here's one way that we write the second derivative, we write it as this d squared y over dx squared. The process is you're going to take the derivative of the first derivative, which you would expect. So whatever you got for your dy dx, you're going to take the derivative of it. It is in terms of t. That's what this numerator means. But then you're not done. You then have to take that and divide by the x derivative in terms of t. So it's the derivative of dy dx in terms of time or terms of t divided by the x derivative. So I kind of put a little note here. You're taking the derivative of what you got before. So the derivative, it goes on top, and then you're dividing it by dx dt. So I want to take you through some practice examples, and we can also do some together as far as AP problems. So let's say we have an x equation that is sine of t, and we have a y equation that is cosine of t. And the problem wants us to find both the first and the second derivative. Often on the AP test, you'll see a lot of multiple choice questions like this, and they usually only ask for one or the other. But I'm going to get in the practice of finding both because you never know what they're going to ask. So for your first derivative, you're going to take the derivative of the y first. So your derivative of cosine is negative sine. And then you're going to divide that by your x derivative, which in this case, the derivative of x is cosine of t, sorry, not x. You can simplify it. If you can simplify it because you are going on and doing another derivative, I would. So you should know that sine over cosine is tangent. So your first derivative is tangent, negative tangent of t. So that is your first derivative, and it would be used to find something like slope at a particular time. To find the second derivative, now we're going to derive this. So the derivative of tangent is secant squared. It keeps the negative. So the derivative of the derivative is negative secant squared. And then you're going to divide it by your original dx dt, which was cosine t. Now that can actually simplify as well because cosine and secants are reciprocals. So if I take a secant squared and I divide it by a cosine, you're just putting another secant there because cosine is the reciprocal of secant. So this could actually simplify way down and give you negative secant cubed of t for my second derivative. So again, first derivative, super intuitive, super quick. Derivative of y over derivative of x. Second derivative takes a little more work, a little more process. It's the derivative of that derivative divided by the original dx dt. So let me show you some more. So here's one that asks several questions. So we have to be given the pair of parametric equations. So my x equation is the square root of t, and my y equation is 1/4 t squared minus 4. This particular question wants you to write the tangent line at t equals 1. And then it wants to say, when does it have a horizontal tangent line? And then it wants to say, where does it have a vertical tangent line? I'm also going to talk about concavity with this one. So I've got a lot of questions, so we're going to talk about this one, although they all kind of go together. I want to talk about the concavity at let's do the concavity at 4. So we're going to find the tangent line at 1, the concavity at 4, and when does it have a horizontal and a vertical tangent line. So this is, most of the focus here is going to be on the first derivative. So my dy dt, I can keep the 1/4 out front, and then I can just take the derivative of what's in parentheses. Derivative of t squared minus 4 is 2t. So we're going to get a dy dt of 1/2 t. And then we're going to get a dx dt, power out front, power 1 less. So we're going to write it as 1/2 square root of t. So when I look at my derivative, my overall derivative, dy dx, it's going to be the 1/2 t on top and the 1/2 square root of t on the bottom. We can simplify that. We can definitely break that down a lot. I'm going to keep that to answer some future questions, but we can definitely do some simplifying here. So my 1/2 will actually cancel because I have a 1/2 on the top and the bottom. So now I have a t to the first over a 1/t to the half. If I multiply by the reciprocal, I'm going to get t to the 3/2 as my first derivative. So the first part wants to know what's the slope and the tangent line at 1. Well, if I put 1 in, I get a slope of 1. To write a tangent line, it takes more than just having the slope. You have to have an x and a y. So we're going to have to go back to the original equations and put 1 in to find my x and my y. So if I put 1 in for the square root of t, I get just 1. So my x coordinate is 1. And if I put 1 into the y equation, 1 squared is 1 minus 4 is -3 times 1/4, so -3/4. So my tangent line is y minus -3/4, so that's going to be plus 3/4, equals a slope of 1 times x minus 1. So much easier to do tangent lines in point slope form and leave it, and the AP is very comfortable with that. So we have the slope at 1, we have the tangent line at 1, everything's done on the top. To do the horizontal tangent line and the vertical tangent line, so your horizontal tangent line is when you have a slope that is 0. So when you think about your slope, it's going to be dy dt over dx dt. If the top is 0, you're going to get a 0 slope, which is going to give you a horizontal tangent line. If the bottom is 0, you're going to get an undefined slope or a vertical tangent line. So with this one, let's see, my horizontal tangent line is going to be when this equals 0, which is going to be when t equals 0. My vertical tangent line is actually never going to happen because this will never equal 0 because there is no way to put something and create a 0 because it's in the denominator. So you would only get like an undefined. So you have no vertical tangent lines because, again, this entire piece will never equal 0. You do have a horizontal tangent line at 0. Now for the concavity, so your concavity is the second derivative. So now I have to take the derivative of the derivative. So here was the derivative. I know there's a lot going on my screen right now. So power out front, power 1 less. That's going to be my derivative of my derivative. Divided by dx dt, which was 1/2 square root of t. Now, if you want, you can do a ton of simplifying, or at this point, you can say, you know what, I can just start plugging in the number that I need, and rather than worry about simplifying, I'm going to put 4 in. So if I put 4 into the top, I get 3/2 times 4 to the 1/2. So square root of 4 is 2 times 3/2, I get 3. And if I put 4 into the bottom, I'm going to get 1 over square root of 4 is 2, 2 times 2 is 4. Multiply by the reciprocal, I'm going to get 12. And really with concavity, I'm not as concerned about the number as I am concerned about the sign of it. So positive versus negative. Since I have a positive second derivative, that tells me that this graph must be concave up at t equals 4 because it had a positive derivative. So again, I know there's a lot going on this slide, but it kind of shows you all the things they could ask about the first derivative and the second derivative. There is more about the first derivative because first derivative tells us so much about slope and tangent lines. Second derivative is a little more limited in its usages. Concavity is really the big one. So let me show you another one. Try to write a little neater here. So my equations this time are 4t squared minus 3t for x and 2t cubed minus 3t squared minus 12t. And we're going to do the tangent line thing again. We're going to do the tangent line at t equals 1, and we're going to do the same thing with the horizontal and vertical tangent line, just because it is a common question. Slope is also a common question, or just deriving it. You will have ones that the only thing they want you to do is derive it. We're not going to do the second derivative on this one. We're going to focus all our attention on the first derivative here. So my dy dt is going to be 6t squared minus 6t minus 12. My dx dt is going to be 8t minus 3. So first we'll start up talking about slope. When I put 1 in, my slope, let's see, when I put 1 into the top, I'm going to get 6 minus 12. I'm going to get negative 12. And when I put 1 into the bottom, I'm going to get 8 minus 3, which is 5. So my tangent line has a slope of negative 12/5. My x value and my y value are going to come from putting 1 into this equation, these equations. If I put 1 into my x equation, I get 4 minus 3, which is 1. If I put 1 into my y equation, I get 2 minus 3 minus 12, which is going to be negative 13. So my tangent line equation is y minus a minus 13, so plus 13, equals negative 12/5, x minus 1. So that's my tangent line equation. Sometimes they'll just ask for slope. Sometimes they'll just ask for the derivative, but if basically the longest they could ask you with something like this is to go all the way to the tangent line. Horizontal tangent line is going to be when the numerator, or the dy dt, equals 0. So I'm going to take 6t squared minus 6t minus 12. This is one that I found in a non-calculator setting because it factors really nicely, so that you can take a 6 out. And then it factors t minus 2, t plus 1. So the 2 times that we have a horizontal tangent line are at positive 2 and negative 1. And then finally so this is horizontal tangent line. The vertical tangent line is going to be when the dx dt equals 0. This actually does happen, not unlike the one before. We're going to add 3 and divide by 8. So it happens when t is 3/8. We get a vertical tangent line. So those are the basic things they could ask when it comes to derivatives. We're going to do some practice together with some AP problems, but you're going to see a lot of questions that either ask you to just take the first derivative, just take the second derivative, or to answer questions about slope, tangent lines, and concavity based on those derivatives.